we can start with the first and only speaker of this plenary session, who is Kelley Hess from Honsala Space Observatory and Chalmers University of Technology. And she's going to tell us about recent results from major H1 surveys. Thank you, Kelley.
Great, thank you very much.
The floor is yours.
Thank you all for coming, and thank you very much to the organizers for inviting me to give this talk. I'm truly honored to be here. It's quite a daunting task to try and summarize the most recent interesting results from major H1 surveys, in part because they're very much ongoing right now, and also because the field, despite being about 73 years old, is advancing especially rapidly now. And I'll point that out in just I'll point out why exactly in just a moment. So throughout this talk, I'm going to use the phrase H1, but what I mean is neutral atomic hydrogen gas. And we trace the H1 content of galaxies through the 21 centimeter spectral line, which is emitted in the radio when a hydrogen atom undergoes a spin flip transition. We care about atomic hydrogen because it's the simplest atom in the universe and also the most abundant. We also think that H1 is an essential phase in the baryonic cycle of galaxies that all gas passes through. The H1 reservoir serves as a fuel for future star formation. And we believe that it collaborates with dust to form molecules. Those molecular clouds can cool and collapse to form stars. Stars at the end of their life recycle gas back into the environment, which of course cools again into H1 to replenish the reservoir to start the cycle again. H1 is also important because it's often much more extended than the stellar disk of galaxies, so it allows us to probe the cold dark matter halo in galaxies, and it's among the most tenuously bound components of galaxies, so it becomes a very sensitive tracer of galaxy, of interactions with the environment. So despite having been studied very well for many decades, incredible strides have been made recently as a result of either upgraded instrumentation to existing telescopes, such as Westerbork and the Very Large Array, or else due to really incredible new facilities that have come online, such as ASCAP, MeerKAT, and FAST. These new facilities have greatly increased our amount of collecting area, for example, such as with the FAST telescope in China. They've greatly increased the survey speed capabilities of H1 surveys, such as ASCAP with phased array feeds. A similar upgrade exists on the Westerbork telescope with phased array feeds. Or, for example, just incredible sensitivity of MeerKAT with also its very clever baseline distribution, which allows us to capture H1 on spatial scales from high resolution all the way to quite broad low column density diffuse gas. In this talk, I'm mostly going to focus on H1 surveys that have spent or been allocated up to 1,000 or more hours on these telescopes. You can imagine that in the parameter space between doing tens of hours on previous facilities versus thousands of hours on new facilities, yes, there's this incredible parameter space and a lot of people doing very excellent work that I simply won't have time to touch on today. And so for those people, I apologize, but there is a lot out there and I encourage you to seek it out yourself. So the first survey that I want to mention, if it comes up, is one called Mongoose. Mongoose is a MeerKAT large survey project led by Erwin de Block, who actually gave a very nice talk yesterday in one of the special sessions. Mongoose is the successor to several earlier targeted deep surveys of nearby galaxies, such as Things and Halo Gas, which you may have heard of. The ultra-deep H1 observations with Mongoose aim to study the cold gas accretion in galaxies and to link that cold gas accretion to this active star formation in the galaxies. It's targeting about 30 galaxies with about 55 hours each with MeerKAT. And really going down to absolutely incredible column densities. The stellar mass of the sample also spans about 3.5 orders of magnitude, so it's studying the star formation rate in a broad range of galactic environments. Sorry, these are big files. Let's try again. All right. So one of the first results to come out of Mongoose was by Julia Healy, looking at this galaxy, NGC 5068. I love this image because it allows me to give you a little bit of a primer for how we think about H1 in galaxies. We use this key parameter of column density to basically describe the sensitivity of our observations. Now, if you can achieve column densities of about 10 to the 20 per centimeter squared, this is a key number. This allows you to trace the main H1 disks of galaxies. This is where about 90% of the total H1 gas in a galaxy resides. If you can go about 2 or 3 times deeper, get down to a few times 10 to the 19, then you get to see the extended disks of the galaxies. In addition to those extended disks, you can start to see the highest density clumps of H1 in the intergalactic medium as well. But at these column densities, you pick up another, say, 10% of the total H1. The sort of best H1 observations, targeted H1 observations of galaxies previously, before Mongoose, got down to about 10 to the 19, or we're scraping the top of about 10 to the 18 atoms per centimeter squared in column density. Mongoose now is tracing down to 10 to the 17 atoms per centimeter squared in column density. And at about this kind of magical number of a few times 10 to the 18, they see really beautiful extended emission. And in this particular galaxy, they see evidence for perhaps either gas accretion or minor mergers surrounding the galaxy, especially up to the northwest, which you can see in sort of the lower right-hand panel. Mongoose is also not only looking at face-on galaxies, but it's also looking at edge-on galaxies. And this is some work by Nikki Zabel, who in this particular edge-on galaxy, you see a whole lot of fluff. That fluff is not noise, that is real gas that they're detecting. And they're resolving the clouds in the thick disk of this galaxy. And these clouds are likely participating in the galactic fountain mechanism, which is basically gas blown out of the disk as a result of star formation that is then raining back onto the gas disk. Not all galaxies, however, in the Mongoose sample show clear evidence for extended H1 emission. And these are 2 face-on spiral galaxies that they've observed. And what they see is that in galaxies that are in more isolated environments, they can probe to quite low column densities, but they see quite a sharp drop-off in the column density, quite steep gradients, I should say, at the edge of these extended H1 disks. It's not until you get to environments where you have more companions where you actually start to see a more extended and more intergalactic H1. And the current belief, although this is still work in progress, is that whether or not you see extended H1 in these galaxies is therefore really an environmental thing, where you really need these companions to also see the extended H1. The depth of the Mongoose observations is such that not only are they getting really exquisite images of their main targets, but they also detect a whole lot of the dwarfs around these galaxies, as is evident in the right-hand picture. And the depth is such that actually they're starting to detect the lowest H1 mass galaxies in these external galaxies that are comparable to the lowest H1 mass galaxies in our own local group. And in fact, dwarf galaxies are going to be kind of a bit of a theme that you'll see recurring in the rest of this talk, which H1 surveys are allowing us to learn a lot more about right now. On the theme of understanding sort of the extended emission in these galaxies, I also want to point out some results from a survey called FEAST, which is mapping H1 in galaxies and galaxy groups with a FAST telescope. They use this large single-dish telescope in China to map the extended H1 around systems, and they see vast amounts of H1 that's quite extended. Its collecting area allows it to achieve similar depths to Mongoose, but in a fraction of the time. And what they see here is that these extended H1 reservoirs shouldn't be very long-lived. They should evaporate quite quickly. And the fact that they're somewhat ubiquitous, especially in interacting systems, they hypothesize that perhaps turbulent mixing in these systems, perhaps through interactions between the galaxies, is actually inducing H1 cooling and creating these massive reservoirs that they see. So that's pretty exciting. Again, you have to go to sort of very low column densities to see this. You need sensitivities of about 10 to the 18 per centimeter squared before you can start to detect these things. As we sort of move up the dark matter halo mass distribution, if you will, another pointed or targeted survey, I should say, with Meerkat is the Meerkat Fornax survey. This aims to study galaxy quenching in a small cluster. Now, Fornax is quite an interesting cluster because it's quite low mass for a cluster. It's about, say, 5 times 10 to the 13 solar masses. It also has an incredibly large population of dwarf galaxies. It's something like twice the number of dwarf galaxies as compared to Virgo, and a much higher galaxy density and dwarf galaxy density, indeed. And so the status of the Fornax survey is that in the north east side, you can see that they've got about 60% of the survey, which is science ready. In fact, they started their observations during Meerkat science commissioning with Fornax A down in the southwest. In a series of papers, I quite like this because they show in a series of papers the complementarity between H1 spectral line observations, radio continuum observations, and radio polarization observations, all that are collected in the same observations. They show that there's H1 debris around Fornax A that's consistent with a previous merger history. They see that the AGN is flickering and discuss the feeding and feedback mechanisms that are happening in this system. What's also particularly interesting is that these giant radio lobes that you see in red, they're also polarized. And so they can see depolarization of those lobes that's being caused by foreground H1 clouds that live in this environment as a result of that past merger activity. And I think that's pretty cool. To the northeast, as I said, this Fornax survey is about 70% complete for science. And since Fornax has this incredible dwarf galaxy population, in fact, it's for the most part dominated by early type dwarfs, but recent work by Dane Kleiner has closely examined sort of the late type dwarf galaxy population as well, and found that the dwarf galaxies in Fornax, despite it being a fairly low mass cluster, they lose their gas on incredibly fast timescales. The gas disappears within an estimated something like 240 mega years. And so what I'm showing here is you can see the X-ray contours of the cluster in pink and the H1 contours of the H1 detections in green. In addition to sort of studying those late type dwarfs, they've also discovered sort of 6 galaxies that have these one-sided starless H1 tails. These tails, they believe, are traced by, I should say, shaped by ram pressure. However, the galaxies themselves, out of which these tails are originating, have very disturbed stellar disks. And so the conclusion here is that actually pulling gas out of these galaxies in Fornax is really a 2-step process. It requires tidal interactions first to sort of stir up the gas in these disks to create and to pull some of that gas to quite large radii before it is then experiences ram pressure as a result of the galaxy's motion through the cluster environment. There's one actually very good, very detailed example, which is in a paper that's about to be accepted by Paulo Serra. This is NGC 1427. And what you see here is that on the right-hand side, I'm showing a position velocity diagram with position on the x-axis and velocity on the y-axis. You see that this position velocity diagram slices through the major body of the galaxy, the main body of the galaxy, which you see in red. You see that there's a twist in the velocity profile, which the authors attribute to tidal interactions, but then as you go from the main body of the galaxy to the left, you see a long velocity gradient, which is the tail that's being shaped by ram pressure. And so the emphasis really here is that in this low mass galaxy cluster, removing gas in these galaxies is this two-step process of tidal interactions and then ram pressure. These, both Mongoose and Fornax are very much ongoing. In fact, that's going to be a common theme throughout the rest of this talk and for all of these surveys. And so these are really just sort of the early highlights, and there's certainly more to come. In addition to the spectacular observations we get from these targeted surveys, there are several wide areas H1 surveys that are ongoing or sort of recently completed. On the left-hand, and the two that I'm going to talk about are Aperitif and Wallaby. On the left-hand side, I'm sort of comparing Aperitif and Wallaby to what was the state of the art in about 2018, which were High Pass and Alfalfa. Now, High Pass and Alfalfa were single-dish H1 surveys. They detected about 40,000 galaxies in the nearby universe, out to about a redshift of 0.06. And Aperitif and Wallaby can really be seen as the successors to High Pass and Alfalfa. And that's because these are on interferometers, which allow us to resolve the H1 emission in nearby galaxies, which was not previously done with a single dish. The Aperitif and Wallaby are both on telescopes that have phased array feeds, which greatly increase the survey speed, which is why we can cover large areas. They have large fields of view, which allow us to cover very large areas on the sky. They're also going out to a redshift of about 0.1 or just below 0.1. And what's a bit frustrating is that they could go further. They're not actually limited in terms of their instrumentation. What limits the redshift range for many H1 surveys is the presence of radio frequency interference from satellites. And the RFI environment, as we call it, is very hostile beyond a redshift of 0.1. So Wallaby in the south, in the southern hemisphere, what I'm showing in pink, it has released data from its pilot survey, which is basically the sort of 7 pink blocks that you see. And it's really now just starting its full survey mode. Aperitif, which I'll talk about second, is in the north, and those are sort of the blue points that I'm showing. So Wallaby observes every field twice with offset pointings so that it evens out its survey coverage, its sensitivity across the field of view. And these pointings cover about 36 square degrees at a time. So just for comparison, I'm showing the size of the full moon compared to the snapshot field of view of ASCAP, of Wallaby. Well, yeah, ASCAP and Wallaby survey. The pilot survey has been going for a while, but I wanted to highlight a couple of their recent major successes. They had a couple of press releases last year. One was that they discovered a fast radio burst, and they actually localized it to a gas-rich spiral galaxy. This is interesting because we don't really know where fast radio bursts come from, and locating their host galaxies and the property of the host galaxies holds some clues as to what they might actually be. I emphasize that Wallaby is also able to resolve the sources that it detects, and so they also had a press release about the discovery of 2 polar ring galaxies last year that were revealed in H1 and were not previously known from their optical imaging. I mentioned that they've released their pilot survey data. This covers about 360 square degrees around interesting areas of nearby large-scale structure, and it includes about 2,400 H1 detections. In fact, they've also released the kinematic models for a handful of these, well, quite a large handful of these galaxies as well. They can fit kinematic models to about 10% of the H1 sources that they detect. This is, well, I'll emphasize this again, but this is particularly interesting because with Wallaby and Aperitif, finally we are going to have sort of the statistical numbers to, do statistics on rotation curves and the detailed kinematics of galaxies in the nearby universe. Moving on to Aperitif. Aperitif is in the north, This is also a survey on an instrument outfitted with a phased array feed. Again, now a snapshot covers about 8 square degrees. Again, comparing the field of view of Aperitif to the full moon. And the whole goal of Aperitif and Wallaby is really to provide an unbiased view of the H1 in the local universe. And so what I'm showing here is just sort of a random field, not so random because it's one I actually really like, but it's got about 87 H1 sources in here that are detected over a very limited redshift range. And it shows the discovery of an H1 gas-rich group. And this data, of course, is also 3D. And so what I'm showing on the right-hand side are 3 galaxies and all of the gas that's flowing between them as a result of their interactions. And so these streams really sort of trace the history of their interactions. We are headed towards data release 2 for Aperitif. Data release 1 happened a couple years ago. Data release 2, we're trying to put out all of the calibrated data products and images, but we are still working on towards H1 advanced data products, and that's probably a few years down the line. So let's see if I can get out of that. But just to sort of give you an idea about what Aperitif and also what Wallaby is detecting. In Aperitif, we've detected about 6,500 H1 galaxies so far in about 13% of the total data volume that we have. We pick up lots of very faint dwarfs. We primarily are dominated by blue star-forming galaxies, but we also see H1 in a lot of early type galaxies as well. And so this is just a random selection of things that I've picked out that I thought looked interesting and sort of showcase the range of detections that we have. In fact, Aperitif is actually made up of 2 H1 surveys, which I will show here on the next slide in a moment. Perhaps. There we go. It's got a wide field component as well as a medium deep component. And the wide field covers about 2,200 square degrees down to a column density of about 10 to the 20, which, as I said, is about where you can reliably detect the main disk of galaxies. The medium deep survey goes about a factor of 3 deeper, so a few times 10 to the 19, so it really traces the extended H1 emission around galaxies and in interactions. We can also smooth this data to get to even lower column densities. On the right-hand side, I'm just showing a stellar mass versus star formation rate plot using points from Leroy et al. 2019. And in collaboration with Antonino Marasco, we have a program to measure the stellar mass and star formation rate for all of the Aperitif galaxies. And so here what I'm showing is that the Aperitif galaxies really do sort of trace the main sequence, but we also detect galaxies that are quenched and have H1, and we also push down to quite low mass. Our H1 selection picks out a lot of very low mass dwarfs that might otherwise be ignored or not have, for example, spectroscopic redshifts in optical surveys. With the help of Konstantin Hobner, who's a PhD student with Federico Lelli, we're also attempting to get kinematic models for as many H1 sources as we can in Aperitif. Currently, we estimate that about 25% of our current sample have sufficient signal to noise and resolution for rotation curve fitting. So that's about 1,800 galaxies for which we will have hopefully good kinematic models. I'll also say that so dwarfs are also very interesting. Like I said, we sort of preferentially select for these things in the local universe. So there's work that's recently submitted by Barbara Seljig, who's at Kaptein Astronomical Institute, where she looked at an H1 selected sample of dwarf galaxies. She's found that the H1 selected sample, the standard dwarfs tend to follow the baryonic Tully-Fisher relation, which I'm showing on the right-hand side. But we also find UDGs in that H1 selected sample, and they tend to be offset on the baryonic Tully-Fisher towards lower rotational velocities. This is also what's been found with previous studies, but this is essentially a new way of selecting and studying studying dwarf galaxies. Interesting, she also finds a very high fraction of dwarf galaxy pairs in our H1 selection, and this is actually going to be the subject of her next paper. Okay, finally, I'll talk just a little bit about H1 deep field surveys. The goal here is to try and understand how the gas reservoir of galaxies evolves with redshift. And I realize that high redshift means different things to different people. And so for the Chiles survey, we go out to a redshift of 0.5, and for Laduma, we go out to a redshift of about 1.4. The goal is that on the right-hand side, I'm showing that what we know about the H1 content of galaxies is limited to the local universe in terms of what we know from direct detections. Most of the points on that plot beyond a redshift of 0.1 actually come from absorption line measurements and samples of damp Lyman alpha. And so you may say that 0.5 and 1.4 is not very high redshift, but the important point here is that Chiles and Laduma actually are probing the region where we see very steep drop-off in the star formation rate in the universe after cosmic noon. So Laduma is also a survey with Meerkat. It's a single pointing in the Chandra Deep Field South. It's very much ongoing, and we're working towards our first data release. It's got about 200 hours in L-band so far, and nearly 900 hours in the higher redshift band at UHF. And we've got about 200 H1 detections below a redshift of 0.1 in the first sort of 120 hours of time on source. I won't go into too much detail, but there is very excellent work by a couple of grad students, Amir Kazemi Moradani and Munira Hussein, who are working on, the first is creating the first Laduma H1 mass function, and the second is looking at using H1 stacking to get the average properties of galaxies out to quite high redshift and extending all the way out to a redshift of 0.5. Finally, I'll mention Chiles. Chiles is a 1,000-hour survey with the VLA. We've got a catalog of about 100 detections in 800 hours of observing. Chiles is a much smaller field of view than Laduma, and so we actually do expect to detect fewer H1 detections. Chiles actually currently holds the record for the highest redshift H1 detection at a redshift of 0.376, although a couple months ago that was recently overtaken by FAST, and I'll show that in a moment. Something I want to point out is that, how am I doing? Oh, yeah. I can, okay. Something that I mentioned before is that H1 observations are severely impacted by radio frequency interference between a redshift of 0.1 and 0.2. And despite that, with a lot of painstaking work, we've actually recovered about 14 H1 detected galaxies at a redshift of 0.1 in a cosmic wall. This is interesting because we then went after them with ALMA, and we detected the top 5 with ALMA. So we have the first resolved measurements of both atomic and molecular gas in galaxies beyond a redshift of 0.1. And this is just to show you the kinematics of those galaxies. We see that the CO traces obscured star formation in the central parts of the galaxies, and the H1 traces the extended H1 disks, but the kinematics agree fairly well. Just to say that I mentioned FAST actually now currently holds the record for the highest redshift detections in H1 with 6 record-breaking detections at a redshift of 0.4. So incredible telescopes are contributing to giving us really incredible data. And so there is a whole lot more to come with SKA on the horizon. But I'll leave you with sort of just a summary of the major ways in which we're making enormous strides in current H1 surveys. Thank you.
Thank you very much. We have time for one question, one quick one. Yes.
A quick one and a naive one. Would you be able to detect H1 in a pristine form without any stars being formed in a galaxy that hasn't even formed stars?
If it exists, yes, absolutely. Especially with the depth that the current surveys are reaching. Mongoose, for example, and also FAST. That is quite a challenge because you have to convince yourself that it's real. And so you need quite high signal to noise observations. And I think you also need to know quite a bit about what's going on in the environment around it, because many of the starless clouds that we see are later traced back to likely interactions. And so we don't yet know if there is, to what degree there is pristine gas out there lurking. Yes, thank you.
Okay, let's thank our speaker again. Thank you very much.